In Calculus 2, we're looking at section 7.1, which is kind of a formal definition of the logarithm. You know some of this stuff the way that from your pre-calculus class, we kind of just define the logarithm for you. We just give it to you. In this section, we're going to look at the logarithm and the exponential a little bit more carefully, and mostly we're going to just practice a bunch of integration problems. So you should kind of enjoy this section, I think, if you're into the little puzzles of integration. So just looking at the notes from the textbook, we actually in calculus can define the logarithm. In pre-calculus, you define the logarithm as the inverse of the exponential, and the exponential we just sort of came about with. I mean, the exponential function e to the x. But in a rigorous calculus approach, what they actually do is they look at the logarithm as the definition of the integral from 1 to x of the curve or the function 1 over t dt. That's the ln of x. And so when x is positive, it's really talking about the area under the curve 1 over x between 1 and whatever the x is. The reason they have the t here is because it's kind of your dummy variable. It wouldn't make sense to have an x here as well. Okay, so I remember when I was in my undergraduate mathematics, and this is a story that I will tell you because I don't want you to ever have this experience like I did, but I was very insecure in my math. I mean, I knew it and I was a good student, but I was still kind of, humbled by my professors, and I just thought they were all geniuses. And I had a question on a problem. I'm like, I didn't know this question, and it came up, well, the professor, and I always felt nervous going to the instructor, and I said, I'm having problems on this question. He said, well, what's the graph of 1 over x? And I looked at him and I couldn't tell him. And that, to be fair to me, that was in the day when we just didn't have graphing calculators, and I didn't have a teacher. I had great teachers, but I didn't have one that just forced images of different functions in my head. And so because of that, I remember being so embarrassed because he's like, you're a math major and you don't know what the graph of 1 over x, because he really called me out, and I was really humiliated. So at the time, I'm like, okay, now I know it, but I thought it was lame, like who really cares about the graph of 1 over x? But the truth is, the logarithm function is defined to be the area under the curve 1 over x. So it's very important. You remember, just for reference, 1 over x is that function that looks like this, and then it actually has a negative part here. But for our logarithm function, we're just going to define it from 1 to some value x. And when x is positive, you have this area right in here. So it's the area under the curve. I mean, it's huge if you're going to talk about logarithms, that you should know what the graph looks like. So that's why he gave me that look. Now, notice if you're between 0 and 1, then you're going to have the negative of this area. You're going to get this area, but you may remember from some of your stuff, how that, if you go from, like if x is between 0 and 1, then that would mean that this higher limit, the upper limit, is less than the lower limit. And so you remember from Cal 1 that we could put a negative and flip that. And so it actually gives the negative of the area. Now, the function is not defined at, you can't take the ln of 0, and you can't have negative x's either. So it's only for x is greater than 0, obviously not including 0. And if you, on your calculator, the ln of 0 is undefined. And you can see, because if you were at 0, this area goes without bound, so it doesn't make any sense. And obviously, if x were 1, the ln of 1 is 0. And we learned that property, the integral from 1 to 1 is always going to be 0 when you don't have any width. Okay? So that's our sort of formal definition of the logarithm as we describe it in calculus. Now, what's interesting, so then what we do in calculus is we go from the logarithm to the number e. Instead of in pre-calculus, you guys, we learned about e to the x, and then we told you that the ln x was the inverse function. So I'm going the other way. It turns out that e, that 2.7818, that number, is the number, the value of x, such that this area underneath the curve is exactly 1. So it's kind of interesting. And so that is the ln of e is the integral from 1 to e of 1 over t dt, and it equals exactly 1. And so that's why the ln of e is 1. And so from that, you can you can do a lot of neat stuff. All right, so you kind of already know this. The derivative of the natural log is 1 over u, and then here's the chain rule, du dx, right? So if it was ln of x squared, you'd have to do 1 over x times 2x. Or you could use properties of logarithms to simplify it first. And then they do the ln at absolute value of x, of course, is just 1 over x. All right, these are some properties of logarithms. You may remember these from your previous coursework. This is the sum formula, and here's the difference formula, and then this is I don't know if you guys remember, you can write this as ln 1 over x is x to the negative 1 power, and then you can, this is the power rule, brings it in front here, so this is negative 1 ln x. So this is actually called the product rule. It's a different product rule. It's not the derivative product rule. It's the product rule for logarithms. But the ln of a product is equal to the sum of the individual logs, and the ln of a quotient is equal to the difference of the individual logs. So this is the quotient rule. And you can, if you want to read these proofs, you can read them in your textbook, and they use the definition that we did for the integral here. Okay, so again, the integral of 1 over u du is just going to be the ln of the absolute value of u. But because u can't be negative, because you can't take the log of a negative number, and you can't take the log of 0. Okay, and so then here's just this idea that if you have the function y equals ln x, the inverse function is x equals ln y, which turns out to be e to the x. So you have these properties, e to the x and ln x. If you do e to the ln x, they kind of undo each other and you just get x. And if you take the ln of e to the x, again, you just get x. Okay. The beautiful thing about the exponential function is that when you take its derivative, it's just itself, but of course you have to take the derivative. You have to use the chain rule. So, and then the other beautiful thing about the exponential function is that when you integrate it, you do just get back to e to the u. Okay, then you have, these are also familiar probably from pre-calculus, the sum formula or the product rule for exponents, and then here's a quotient rule and just some different formulas that you should be familiar with. Okay, and then it turns out that you don't have to deal with just e to the x. You can be dealing with a different number, or e to the u. You can be dealing with a to the u, and then here's your derivative of a to the u is going to be a to the u ln a du dx. And we did these in calculus 1. And the integral is a to the u ln a plus c. All right. There's two functions, y equals 2 to the x, and here's its inverse, y equals log base 2 of x. And just some properties as you extend it to log base a instead of ln, of course, is log base e. Okay, and then here's your product and quotient and reciprocal rules. Okay, so now that you feel somewhat reviewed on these functions, all I did was just grab the homework problems out of the textbook, and I thought we'd just work as many as we could until I got sick of them. But, or just, I don't know, I don't know if you want to do all the evens or something like that. We can just get busy on working some of these problems. So let's do that. Let's try like number 2. The first thing I would do with number 2 is I would factor the 3 out in the front. So I'm going to do 3 times the integral from negative 1 to 0 of 1 over 3x minus 2 dx. And then you can do a u substitution here. U is equal to 3x minus 2. So du is going to be equal to 3 dx, right? So, you actually have the 3 dx right there, so maybe I shouldn't have factored it out first. Leave it here. My 3 dx is right there, and I have my 1 over u. Now, I like to change my limits of integration. So, I'm going to change my limits. When x is -1, u will be 3 times -1 minus 2, which is -5. And when x is 0, u will be -2. And then this is 1 over u du. But the integral of 1 over u is just the ln of u. So this is just going to be the ln of and then you can't take the ln of a negative number, so this is going to be the ln of the absolute value of u. That's what this is, evaluated between -5 and -2, so this is going to be the ln of 2 minus the ln of 5. Okay, and then you might remember that you could write this as a single logarithm with the quotient rule as just the ln of 2 this. Does that make sense? Okay, so let's do number 4 then. I'm going to come down here, give myself some room. Okay, so number 4 is the integral, I don't know how many of these I'm going to do, the integral of 8r over 4r squared minus 5 dr. So we'll make a u substitution. We'll say u is equal to 4r squared minus 5. So then du is equal to 8r dr. And then that's nice. This will be replaced right there. So it's just going to be the integral of 1 over u. So this is going to be the integral of 1 over u du, which is just the ln of the absolute value of u, where u here was 4r squared minus 5. So this is the ln of the absolute value of 4r squared minus 5 plus c. Okay? All right, let's try number 6. It says the integral of the secant y tangent y over 2 plus secant y dy. And again, you'll probably get sort of a pattern here. What's your u going to be? 2 plus secant y. And the derivative of the secant y is, derivative 2 is 0. Derivative of secant y is secant y tangent y dy, which is exactly what we need. So we're going to get 1 over u du, which is just going to be the ln of the absolute value of 2 plus secant y plus c. Okay? So now we could look at number 8. Is the integral of secant x dx over the square root of the ln of secant x plus tangent x. This one's much harder. Because it's not real obvious, you know, the derivative of the secant is sectan, but that just looks like a big mess there, so we're going to have to do some real thinking here. Okay, so if we let u equal secant x plus tangent x, which probably would just take some trial and error on deciding what to do, then du is going to be equal to The secant, derivative of secant is secant x tangent x. The derivative of tangent is secant squared x. And then you'll have dx, right? Well, this, you can factor out a secant x out of this, and so you'll have du is equal to secant x times tangent x plus secant x dx. And so you're probably saying to yourself, well, if this is the u, the ln u is here, if here's secant x dx, right? Secant x dx. So I could write, wait a second, when I look at this, tangent x plus secant x, isn't that what u was? Right? So I have to be really snazzy here, all right? So I could say that du divided by u is equal to secant x tangent x. I mean, sorry, it's equal to secant x dx. See, if I divide both sides by this, tangent x plus secant x, then I actually get du over u equals secant x dx. You all okay? Not sad yet? All right, now what can I do with that? Well, I can replace secant x dx with du over u, and then I can put secant x plus tangent x. I can put u right in there. So back to my integrand, I can write this as du over u on the square root of ln u. Okay? Which I can write as the integral of the ln of u to the negative 1/2 power times u du. But if you think about it, now it's almost like you want to do a v substitution. If you let v equal the ln of u, what is dv? What's the derivative of the natural log? Yeah, it's 1 over u du. So u dv is equal to du. Well, that's exactly what we have. I'm sorry. You know, hold on, I got to think for a second.
It'd be easier to start out with turning natural pure on the inside of the square root, turn your natural log into secant x